in LJ Institute of Engineering and Technology in Department of Electronics and Communication. This video is about subject fiber optic communication. So friends, in the last video, you learn about the transmission system, particularly the point-to-point link where the one transmitter and the one receiver would be there and which will make the point-to-point system. So now, the system considerations that you also learn. In this video, we are going to learn the very important part as well as the examination purpose. The examples that can be also asked from this topic, that is link power budget, rise time budget, methods for the design of the optical link and the bit error rate calculations. So this portion that is very interesting as well as very important for the any design of the transmission system. So we are going to start with the study about all this thing. So friends, these all are the budget methods for designing of the optical link. When you will design the system, then you should go for the budget methods, which will gives you the idea about the losses which will be appeared while you will design the system. So whenever any system when we want to design, we need to go for the such kind of the analysis. So very first we are going to discuss, it is about the link power budget analysis. Now, in the link power budget analysis, one first determines the power margin between the optical transmitter output and minimum receiver sensitivity needed to be established or specified BER. So that is the simplest kind of the technique which we need for designing. So in this, the rise time budget analysis, so link budget analysis, rise time budget analysis. What is it? So once the link power budget that has been established, a designer can perform a system rise time analysis to ensure that the desired overall system performance that has been met. So this is the requirement for learning about the rise time budget analysis. So the optical power received by the receiver, that depends on how much power we transmit from the transmitting end. So it's a power transmitter, as well as the various losses that has been included over the fiber. So this is the thing that we need to consider for doing the analysis. So now we are going to start the analysis with the first method. It is the link power budget analysis. So the power received at the output, that must be sufficiently higher than the receiver sensitivity. So that is why we need to consider it, that the diagram which consists of the optical source and the detector is there. Now optical transmitter is there, fine. So what happened, that you know that while the connector, okay, that can be connect with the fiber, there is a fiber fly lead is there, the connector is there. Now when you want to join the two fiber, the splicing that you need to do, so you can see the splices, okay. Then after at the other end, other fiber cable is there, the receiver is there, so a fiber lead, fiber fly lead to it will connect with the photo detector. So what is this? That we need to consider that which are the elements they are connected in this system. So while they are connecting, they are producing kind of the loss into the system. So we need to consider all these things while we are doing the analysis. So it is about the link power budget analysis. So the optical power received by the receiver, that depends on the power transmitted and on the various losses occurring over the fiber. So power received at the output, that must be sufficiently higher than the receiver sensitivity after accounting for the safety margin. So PTX is equal to PRX plus plus ms. What is this? PTX, that is the transmitted power. PRX, that is the sensitivity of the receiver, and CL, that is the total link loss or the channel loss. These loss includes the fiber loss, the splicing loss, okay, then the connector loss, and MS, that is the system's safety margin. So these three things, okay, in the equation are there, which is considered for any loss. Channel loss, that can be expressed as CL is equal to alpha F plus alpha CON, that is the connector, plus alpha splice, okay, that is due to the all splices loss. Alpha F, that is the fiber loss, which is expressed in form of the dB per kilometer, and L is the link length. Alpha connector, that is what? All the connectors which can be connected in your link. So all that connector losses that you need to do the sum, and that summation which will be considered as a alpha CON, and the alpha splice, that the number of the splices are there, okay, in the link. So while we are joining all that the splices, so the sum of the losses at the splices in the link, so that is considered to be as a alpha splice. Now we'll solve the example based on the method, that is the link power budget. What is the example? It is design an optical fiber link for a transmitting 15 MB per second of the data for a distance of the 4 km with BER of 10 raised to minus 9. So here the data that is given to us and we need to find it out. So now bandwidth multiplied by the length. What is it? 15 MB per second multiplied by the 4 km. So 16 megabits per second kilometer. Selecting the optical source. We are selecting which optical source according to the previous data? The LED at the 820 nanometer is suitable for the short distances. So that selection. And this LED generates minus 10 dBm optical power. So selecting the optical detector, pin detector. Okay. So optical fiber that is reliable and has the minus 50 dBm sensitivity. So the selection of the optical fiber, step index, multimode fiber that is selected, and the fiber has the bandwidth length product of 100 megabits per second the kilometer. So link power budget. So we are assuming what? Splicing loss, that is the 0.5 dB per slice, connector loss LC, that is 1.5 dB, and the system link power margin PM, that is the 8 dB. So now the total power loss. So that is the fiber attenuation alpha is F is the 6 dB per kilometer. Actual total loss, that is what? A combination of all. So it is 2 into LC plus alpha FL plus PM. So we are putting that value in the equation. So it is PT is equal to 2 multiplied by 1.5 plus 6 multiplied by 4 plus 8. So it is the 35 dB. So this is the answer, that is the 35 dB. So now the maximum allowable system loss, that is the P maximum. Optical source output power, or the optical minus the optical receiver sensitivity. So P maximum, that is equal to minus 10 dBm minus 50 dBm. So it is the 40 dBm. So this is about the actual loss in the system are less than the allowable loss, and hence the system that is the functional. So this is about the example related to the link budget analysis. Now the next analysis, that is the rise time budget. What is it? So this rise time that gives the important information for the initial system design. It determines the dispersion limitation of the optical fiber link also. Then after it also require after doing the link budget analysis also. So the total rise time of a fiber link, that is the root sum square of the rise time of the which contributor to the pulse rise time design. Okay, so now we will do the few more thing, that is the link component that must be switched fast enough, and the fiber dispersion that must be low enough to meet the bandwidth requirement. The bandwidth for the system that can be assured by developing a rise time budget. So that is the thing. As the light sources and the detectors has a finite response to the input, the device does not turn off or turn on instantaneously. Rise time and the fall time that determines the overall response time and hence the resulting bandwidth. So, a rise time budget analysis that determines the dispersion limitation of an optical fiber link. The total rise time, it is denoted by TSYS, is the root sum square of the rises time for each contributor Ti to the pulse rise time degradation. So now we can say that the transmitter rise time TTX, the group velocity dispersion GVD, rise time that is TGVD of the fiber, the model dispersion rise time T mode of the fiber, and the receiver rise time that is the TRX of the receiver. So now it is determined by the equation, that is root sum square of all rise time. So it is the TSYS is equal to in bracket square root of the TRS square, then after the T mode square plus TGVD square plus TRX square. Putting all the values, so it is the TRX square plus T mode, that equation we need to keep in mind directly. It is 440, okay, the LQ upon the B0 whole square plus D square sigma lambda square L square plus TRX, that is the 350 upon the PL whole square, okay, whole raised to 1 half. This is the equation that we have to keep in the mind about the rise time. We are going to solve the example related to this. For a multi-mode fiber, following parameters are recorded. LED with the drive circuit has a rise time of the 15 nanosecond. LED spectral width is equal to 40 nanometer. Then the material dispersion related to the rise time degradation, it's a 21 nanosecond over the 6 kilometer link. Receiver bandwidth 235 megahertz. Model dispersion rise time 3.9 nanosecond. Calculate the system rise time. So now we can have the various the equations. So what is the TTX? It is a 15 nanosecond. Tmax, that is a 21 nanosecond. T mode, it's a 3.9 nanosecond. So according to the equation of the TRX is equal to the 350 upon BRX. So it is the 350 upon the 25. So answer is the 14 nanosecond. Now the equation, okay, that is the T system, that is equal to sigma I equal to 1 to n TRI square whole raised to 1 half. We are putting all the rise time value. So it is a 15 square plus 21 square plus 3.9 square plus 14 square whole raised to 1 half. So it is equal to the 29.61 nanosecond. So this is the example related to the rise time, link power budget, and do it all the examples related to it for the final examinations. Bit error rate. What is the bit error rate? Okay, that we need to discuss in this particular topic. So a bit error rate, that is defined as the rate at which the errors occur in the transmission system. So this bit error rate, that is what? To the rate at which the error that can be occur in the particular system. So that is denoted by the bit error rate. So in the bit error rate, The bit error rate, that is the number of the bit error per unit time. The bit error ratio, that is the number of the bit errors divided by the total number of transfer bits during a studied time interval. So now, it is a unitless performance measure that is often expressed as the percentage. This error probability PE is the expectation value of the bit error ratio. The bit error ratio that can be considered as an appropriate estimate of the bit error probability. The estimate that is accurate for a long time interval and high number of the bit error. So here you can see in the diagram that how the particular the bit error rate, okay, that can be generated, okay, and one device, that is the device under the test, and the another, that is the generating end, another one, that is the detector end, and the checking of the bit error, okay, that can be performed in the system. So this VER, that is the estimation of the one of the valuable ways of viewing parametric performance of digital communication system at a high speed. So this is the diagram. In that also we can see that how the one pulse, okay, that is coming, okay, and how it can be the error that can be found in the pulses. So it is regarding the bit error rate as well as the system design. So thank you very much everyone.